Here we're going to look at weighted minimum spanning trees. First, we need to start by talking about what a weighted graph is. Up until this point, we've used unweighted graphs where all the edges were the same. But now we're going to address this with a weighted graph by adding a weight for each edge. Okay, so just as we've had in the past, we have circles for vertices and we have lines for edges. But now the line also, the edge, has an additional value. It has a number. Each of the edges here has a number. It's an ordinal number, and it can represent a distance, a cost, a time, temperature, profit, anything where we can compare it using a less than or greater than. Okay? Typically, when we use a weighted graph, we want to be able to minimize or maximize whatever it is we're measuring. Might be distance or time or cost, for example. And note we care about the number, not the length of the line. This isn't a drawing contest. There are lines here that look like they're the same length. In fact, they are the same length, but they have different weights, different numbers associated with them. It's just the way it got drawn. It's not important to solving the problem. All we care about as far as the shape of the line is which vertices it connects. So what do weighted graphs represent? What do we do with them? Well, obviously maps. If you've ever used Google Maps, something like that, you're dealing with a graph and you're dealing with a weighted graph. And you'll notice even with this simple example, the weights can represent different things. I might want the shortest route, but I might be more interested in the fastest route. And they're not necessarily the same. And if I'm an engineer building the roads on the map, I might care more about how much things cost. So, for example, we might get a much shorter route by going direct, but that might take us over a river and we'd have to build a bridge, and that could be expensive. We can use them to figure out model circuits and circuit boards. Social graphs show relationship between people. For example, who knows a person on Facebook? You may have heard of the Kevin Bacon game or the 7 degrees of separation. So we can use graphs to keep track of the connection between people, and we might use weights to tell us something about that connection, perhaps how close it is or how much they communicate. So the number might represent the number of messages they send to each other every week, something like that. We can have knowledge graphs that show the relationship between ideas, diplomatic alignments. Curiously, one of the early usages for graph theory was to model diplomatic alignments between countries. World War I, a lot of blame for the war was placed on countries signing agreements to be allies without really thinking them through very well, and then getting pulled into a war without really thinking about it because they had agreed to back their ally. And graph theory people, early graph theory people, started modeling this in quite a bit of detail with graphs and having arguments that certain arrangements of alignments, certain arrangements of alliances were dangerous because they would encourage a war. We can use them in ecology to show a relationship between species. We can use them in something like disk storage to find the relationship between redundant disk regions. We use them for understanding the web. Google's PageRank, how Google finds the significant pages, shows a relationship between web pages, and we can use the PageRank as the weight on a edge between two pages. So graphs have a lot of uses, and weighted graphs are very useful. They're used for a lot of different things. So now we're going to look at a particular technique that's commonly used with a weighted graph called a weighted minimum spanning tree. You recall not long ago we looked at a minimal spanning tree where we worried about the minimum number of edges we needed to connect all of the vertices. So we know that given 6 vertices, we're going to need 5 edges. But which 5? With an unweighted graph, any 5 would do as long as all the edges, since all the edges were the same. But here, we want to minimize the sum of the weights of the 5 edges that we choose. Now, this is still not guaranteed to give us a unique result. Just with minimal spanning trees for unweighted graphs, we could easily generate all sorts of different minimal spanning trees for a given graph. Here, it won't be it'll be more unique, but as long as we have more than one edge that has the same weight on it, and you can see that's true of several edges here. For instance, we have 2 edges with 7 and 3 edges with 7. We could get different minimal spanning trees that still had the same sum. So how are we going to go about this? How are we going to find the right 5 edges? So this is the basic algorithm to do a weighted minimal spanning tree. We pick a vertex, doesn't matter which one, any of them will work, any of them will give us a result that's equally good. There may be more than one result that's equally good, but it'll give us one of them. Then we list the edges adjacent to that vertex. We pick the edge on the list. We said we listed the edges. We pick the edge on the list with the smallest weight. Notice that should sound familiar. This is an example of a greedy algorithm. We talked about greedy algorithms, and here it's actually going to give us an optimal result. We're going to consistently pick the smallest weight, the smallest edge weight, over and over again from our list, and the end result will be an optimal one. We're going to add that edge and the vertice where it goes to our minimal spanning tree. We'll take the edge off the list. We don't want to be stuck where we tried adding it over and over again. And then we pick the newly added vertex that came because we add the edge, came along with it. And we repeat steps 2 to 7 until all the potential vertices are connected to the minimal spanning tree. So let's try it. So here's the graph we're going to work with. This is right out of the LaFleur book. I figured it was just as easy to use his example, and this way you can compare it to the book. Maybe read his prose if my comments aren't quite as clear as his are. So we pick a vertex, and we'll start with an A. We could start with any of them. I'm starting with A because LaFleur does, but any of them will work. And then we list the edges adjacent to A, which A has 2 edges. It has an edge from A to B, and it has an edge from A to D. A to B has a weight of 6, A to D has a weight of 4. So we'll pick the edge on the list that has the smallest weight. That's that greedy approach. And that choice is A to D. So we'll add that edge and the vertex where it goes to our minimal spanning tree, and we'll take the edge off the list. And that gives us the diagram above where we've included A and D in the edge between the two. That will eventually be part of our minimal spanning tree. Once we get the edge into the minimal spanning tree, we're not going to remove it. It's in there for good. We still have another option, the AV6, which we might use later. So now we go do our repeat. So we take D, we've added D, and we go through and we look at all the places that we can get to from D. We can go from D to B for 7. We can go from D to C for 8. We can go from D to E for 12. And we had A to B for 6 left over. So this is our list. And so what are we going to do? Well, we're going to pick the edge on the list with the smallest weight, that greedy approach. And it's A to B. You might think, well, A to B is the old one, but it's the smallest one, and so that's the one we want to pick. So we add that edge and the vertex where it goes, which is B, to our minimal spanning tree. We take that edge off the list because we don't want to pick it again. We've already added it. There's no point in picking it again, even if it's the smallest weight. So at the moment, our list is D to B, D to C, and D to E. But of course, since we've just added B, we're about to expand our list. So we repeat our steps, and we're going to expand our list based on the fact that we now have B to work with. Note that D to B and B to D are the same edge, so it only goes in the list once. And also note that we already have a route to get to B with a weight of 6, so don't put other paths to B on the list. Paths from B, sure, but paths to B, no. So we're not interested in putting D to B on our list with a weight of 7. Why? Because we already have a way to get to B. And it's a way to get to B that's cheaper than 7. And actually, if we're getting there from A, it'd be 4 plus 7, but we won't go there. The point is, our cheapest way to get to B is 6, and that's already in the minimal spanning tree. So we won't put B to D in our list. So what does go into our list? Well, B to C can go into our list. We don't have a way to get to C yet, and now that we have B, we have a new way to get to C. And we also can go from B to E, and we have that with their appropriate weights next to them. So this is our new list. And so now that we have our new list that takes into account that we can get to B, now we're going to run through our other steps, and we're going to pick the edge on the list with the smallest weight. That is the greedy method, and that's going to be B to E. B to E had a weight of 7. That's the lowest on the list. We add E and the edge onto the minimal spanning tree, and we remove it from the list. So we're coming right along. Now we do a repeat to get our edges. We added E, so we're going to ask what edges can we add because we can get to E. Now E to D is the same as D to E, so we're not going to add it in again, okay? And we already have a route to get to E with a weight of 7, so we don't want to put other paths to E on the list. So we get the following. We had D to C left over, and we can still consider that. We had B to C left over. We can still consider that. But now, because we're in E, we can add the possibility of E to C for 5 or E to F for 7. So this is the list we have to work with. So you're getting the pattern of this thing down. So we're going to look through our list. We're going to look through our list and pick the smallest weight, that greedy approach, and it's E to C. E to C was a weight of 5, and that was the lowest weight. So we're going to add C and the edge to E into our minimal spanning tree, and we're going to take it out of the list. And now, of course, we're going to go on and adjust our list. So note that C to B is the same as B to C, C to D is the same as D to C, C to E is the same as E to C. So adding C, the actual new possibilities are limited. We already have a route to get to C with a weight of 5. We don't want to put the other paths to C on the list. So these are what we have left to consider. We have E to F for 7, or we have C to F for 6. Well, as you might know, we're going to pick the edge with the smallest weight, the greedy approach, and that's going to be C to F. We get to add that edge and the vertex where it goes to the minimal spanning tree, and we remove the edge from the list. And now we realize we're done. All the vertices are connected. We can look at the sum of the weights of the connected edges, and we get 4 plus 6 plus 7 plus 5 plus 6. We get a total of 28. So for a weighting of 28, we can connect all of the nodes. Now, what does the 28 mean? Well, it might be the cost of building the edges. For instance, maybe we're laying out roads in a subdivision, and we don't expect a lot of traffic, but we do have to connect all the lots. Or maybe it's the cost for the cable company to run cables through a network to different houses. That could be it too. It could be a number of things that we want to minimize, okay? And we don't really need to worry about the units, because as long as we minimize them, as long as they're ordinal and we compare them with less than or greater than, and we want to minimize them, we don't really have to care about the units as long as all of the edges use the same units. So our minimal cost in doing this, or our minimal weight, depending on how you want to refer to it, is 28. We connect them all using 28. What if we start somewhere else? Well, since we have multiple edges with the same weight, we might get a different set of edges, but the sum will still be 28. No matter where we start in this graph, by the time we finish, our minimal spanning tree will have a total weight of 28. When should we use this? When should we try using a weighted minimal spanning tree? Well, notice that while we've minimized the overall cost, the weight of the graph, we've not optimized particular routes. For example, in the edges we selected and put into the minimal spanning tree to get from D to F is 28. If we go D to C and then we go C to F, that cost is 14. So if we care about a particular route, we need a different technique. The minimal spanning tree doesn't guarantee that each possible route is the best, only that the overall cost has been minimized. Weighted minimal spanning tree often works when we want a set of vertices connected at a minimum cost. This might be connecting the components on a circuit board where each trace takes time and effort, and we want to minimize the number of traces. The traces are the little silver channels on the back that connect components. It might be running cable TV. We might be not so worried about how many places we hop through as long as everything gets connected. It might be connecting all the lots in a subdivision where we don't expect much traffic. Now, if we're going to have a lot of traffic, we might start worrying about the capacity of the edges, and that might bring us to some different conclusions about where we should build roads. But if there's not a lot of traffic and we simply have to get all the lots connected, then a minimal spanning tree could be a good approach. So what have we talked about here? Well, we introduced the idea of weighted graphs, the fact that we can take our graph and we can add a weight to each edge, and now we can solve a lot of problems that we couldn't with the unweighted graphs. And we looked at a particular technique for minimizing the overall weights or cost of a particular graph called a weighted minimal spanning tree.